I want to start by sort of going over the current definition of climate-smart agriculture, and this comes actually from one of the several documents that have been circulated by the Climate-Smart Agriculture Alliance. And the current, the latest definition that I've seen is this sort of relies on three pillars: sustainable increase in agricultural productivity. Then there is adapting and building resilience to climate change and mitigating greenhouse gas emissions. I have a few problems with this definition because, particularly when we're talking about resilience, we see that immediately you have resilience and adaptation coupled in the same sort of one of the pillars. And a lot of people I've noticed in the climate change community talk interchangeably about adaptation and resilience, and I tend to disagree with that, and so it creates confusion. Either they're the same thing, but if they're not the same thing, resilience becomes almost like a fourth pillar of the definition of climate-smart agriculture, which makes things even more complicated in terms of being able to deliver, finding the systems that deliver as far as climate-smart agriculture. And so I like to make this distinction between resilience and adaptation. And I consider resilience as a characteristic of the system, while instead adaptation is what you do to improve resilience. So, and this also provides me an opportunity to more easily create a baseline, which the resilience of the current system, however I define resilience, is my comparison frame. And for this, to make this comparison, this connection, I'm going to use an empirical study that we are finishing for a current project in India. It's for ACR, and the project itself actually targets emissions and emission reductions, and it considers a period that goes from 2010 to 2050. And the modeling structure is quite complicated, and we don't have time to go over it, but it combines several modeling techniques. Our flagship partial equilibrium model of agricultural commodities impact, then there is a land use change modeling component that connects with impact, and then this crop model, DNDC, that allows us to do some sort of greenhouse gases changes, greenhouse gas emissions, and changes in emissions, and changes in soil organic carbon. At any rate, for this particular set of results I'm going to present and then sort of motivate my conclusions, we mostly rely on the results of DNDC. There's a crop model, and so we get yield changes, we get changes in the fluxes of greenhouse gases, and changes in soil organic carbon. And we use some basic data in terms of prices and production costs in order to derive some make some economic statements. In our simulation, we consider 9 common cropping systems. This is what we have sort of determined as being sort of the most common cropping systems in the various states, and the alternatives to the current practices. And as far as our simulations, we have simulated the conventional, so the current system, and then after some first screening, we have identified 3 alternative practices that seem to be particularly promising in terms of reduction of greenhouse gas emissions. No-till, alternate wet and dry, and a combination of no-till and organic fertilizers. Out of this, and all this modeling sort of work, we actually get sort of maps of technical mitigation potential, and these are a pixel level. The pixel in this map is 10 by 10 kilometers squared. So we know even geographically where sort of things happen. We know where the mitigation potential is higher, and we can identify the best practices for a particular location. Out of all this modeling work, we can extract quite a bit of data, actually. And for for this climate smart agriculture component that I'm going to discuss now, we get the effective adoption of those particular mitigation practices on yields, on global warming potential, on soil organic carbon, changes in soil organic carbon, and in net revenues. And after that, so we're thinking about climate smart agriculture, and we look at those three pillars, right? So we have a sustainable increase in productivity, adaptation, and mitigation. And we know that actually, when we talk about sustainable production, there isn't just one thing that contributes to sustainable production. There are several components in the system that can contribute to that. So given the data, I'm trying to characterize each single component and try to see sort of what the different practices, how they contribute to the system. So, and I'm considering, for instance, for a sustainable increase in productivity, I'm considering the output, so changes in yields compared to the baseline, which is the current output, and changes in soil organic carbon. And here I actually have numbers, but I've used like a pretty simple sort of ranking system for which, I have sort of plus signs mean that I'm doing better than the baseline, minus signs means that I'm doing worse than the baseline, and then sort of rank across options. So I can do that for sustainable increase in productivity, and then if I think about adaptation and what contributes to the capacity of a production system to adapt, I consider soil organic carbon and net revenue, so there's an economic component and a physical component in this capability. And then mitigation, it's a little simpler because basically I only have global warming potential. So from this, I'll try to rank the different practices and see which one is better in terms of climate smart agriculture. Well, and it seems that, at a first analysis, it might seem that no-till is the best one, but things are obviously a little more complicated because it actually depends on where you put the emphasis. If the emphasis goes, for instance, instead of sort of sustainable productivity, it goes on reducing global warming potential, well, you could see how alternate wet and dry might be a better system. So where you put the emphasis and the weights that go in the different sort of contributions really makes a difference. Now, where does the resilience come from? So what we did, we looked at we simulated some climate extremes. We basically simulated different weather realizations, and we picked basically the tail ends, and we considered the performance of the different practices and how they deliver, given this sort of particularly extreme sort of set of climatic realizations. And we look at yields, how they perform, how the different system performs in terms of yields, and yield variability. And so we formed this also we try to measure how these systems, cropping system performs for resilience, and we see that. So we try to rank them, and it appears that the no-till is doing better than others, but it needs to be cautioned because one important factor that needs to be considered is the fact that no-till generally has an initial period in which returns are lower than the existing systems in the status quo. And so there is an investment that is particularly important. It's given the analysis, the analysis results actually tell us that it's very difficult to make blanket statements on what actually works and what doesn't work, particularly when you include in climate smart agriculture this additional component that is resilience. And this type of multi-objective analysis become complicated very quickly, and so it makes it even harder to make policy recommendations.
Thank you so much, Alex.